For most of human history, time stretched endlessly in both directions. Ancient civilizations gazed at the stars and saw not a universe with a beginning, but an eternal dance of lights across an infinite sky. The Babylonians, with their precise astronomical records, believed the heavens cycled forever without start or finish. Hindu cosmology spoke of vast cycles lasting billions of years, each universe dying and being reborn in an endless rhythm. Greek philosophers like Aristotle argued that the cosmos must be eternal, for how could something come from nothing? This view of eternal time felt natural to our ancestors. After all, what they could observe seemed permanent. The sun rose and set with clockwork precision. Seasons cycled reliably year after year. The same constellations wheeled overhead that their grandparents had seen. If anything changed, it changed so slowly as to be imperceptible within a human lifetime. The universe appeared not just old, but timeless. Religious traditions offered different perspectives, but even these often struggled with the concept of cosmic beginning. While the book of Genesis spoke of creation in 6 days, early Christian theologians like Augustine wrestled with what existed before time itself. Buddhist cosmology described eons upon eons, with universes expanding and contracting in cycles so vast they defied human comprehension. Even when cultures imagined beginnings, they often imagined them as part of larger eternal patterns. The first serious attempts to put numbers on cosmic time came not from observation, but from interpretation of texts and genealogies. In 1650, Archbishop James Ussher famously calculated from biblical chronologies that creation occurred on October 23, 4004 BC at 9 in the morning. His precision was remarkable, his confidence absolute, and his method entirely wrong. But Ussher was working with the best tools available to him, tracing lineages and adding up generations in sacred texts. Similar attempts emerged from other traditions. Ancient Chinese astronomers calculated cycles of cosmic renewal spanning tens of thousands of years. Indian mathematicians worked with numbers that made European scholars dizzy, describing cosmic ages in millions and billions of years. Yet all these calculations shared a fundamental limitation. They were based on human records and mythological accounts, not physical evidence from the cosmos itself. The breakthrough came slowly, as it often does in science, through a gradual shift in thinking about what kinds of evidence matter. The first hints appeared in geology, where careful observers began to realize that rock layers told stories spanning far longer than any human chronicle. James Hutton, studying Scottish Highlands in the 1700s, saw in the stones evidence of processes so slow and gradual that they required what he called deep time, periods almost unimaginably long compared to human experience. But geology, revolutionary as it was, dealt with Earth's history. The cosmos remained mysterious. Even the greatest minds of the Enlightenment assumed the universe as a whole was eternal and unchanging. Newton's laws described motion beautifully, but they worked equally well whether time ran forward or backward. The gravitational dance of planets could continue forever, neither beginning nor ending. This perspective began to crack in the 19th century as physicists encountered thermodynamics, the science of heat and energy. If the universe were truly eternal and unchanging, why hadn't all energy already spread out evenly? Why were stars still burning instead of having exhausted their fuel eons ago? The second law of thermodynamics suggested that isolated systems always move toward greater disorder, toward what physicists call entropy. An eternal universe should have reached maximum entropy long ago, becoming a cold, uniform, lifeless void. This thermodynamic argument pointed towards something startling. The universe must have had a beginning, a moment when energy was concentrated and order was high. The cosmos wasn't eternal after all. It had an age, a finite lifetime that could, in principle, be measured. The realization that the universe might have an age rather than existing eternally was perhaps one of the most profound shifts in human thinking. It meant that cosmic time wasn't just the backdrop against which events unfolded, but was itself part of the story. Time had a beginning and possibly an ending. The universe had a history, with chapters and turning points, growth and change. Yet knowing that the universe had an age, and actually measuring that age, were very different challenges. How do you put a number on cosmic time when your instruments are confined to one small planet, orbiting an ordinary star? How do you measure distances and times so vast that light itself, traveling at 300 million meters per second, takes billions of years to cross them? The answer would come from an unexpected direction. The key to measuring cosmic time wouldn't be found in the ticking of clocks or the decay of radioactive elements, though both would play supporting roles. Instead, it would emerge from understanding the most fundamental force shaping the cosmos: gravity. Gravity, which keeps our feet on the ground and planets in their orbits, also governs the largest structures in the universe. It pulls matter together to form stars and galaxies. It bends space and time according to Einstein's theories. And it controls something even more remarkable: the expansion of space itself. This expansion, first glimpsed in the early 20th century, would prove to be the universe's master clock. By understanding how gravity has driven cosmic expansion over billions of years, scientists could work backward to find when expansion began. They could measure the age of everything that exists. The story of how we learn to read this gravitational clock is one of humanity's greatest intellectual achievements. It combines the most abstract mathematics with the most precise observations, the grandest philosophical questions with the most detailed experimental work. It reveals how the force that makes apples fall also shapes the destiny of galaxies and encodes within its equations the very age of time itself. In the chapters that follow, we'll trace this remarkable journey from Newton's first insights about universal gravitation to modern precision measurements of cosmic age. We'll see how gravity serves as both the engine of cosmic evolution and the key to understanding cosmic time. We'll discover that measuring the universe's age isn't just about satisfying human curiosity, but about understanding the deepest nature of reality itself. The universe, it turns out, is not eternal. It had a beginning, and that beginning can be dated with remarkable precision. The clock that measures cosmic time isn't made of gears and springs, but of curved space-time and gravitational fields. And learning to read that clock has been one of our species' most extraordinary accomplishments. Isaac Newton sat beneath an apple tree in 1665, or so the legend goes, when a falling fruit sparked one of science's greatest insights. Whether the apple actually fell on his head matters less than what Newton understood in that moment. The same force pulling fruit earthward also holds the moon in its orbit around Earth, and Earth in its dance around the sun. Gravity wasn't just a terrestrial phenomenon, but a universal principle governing all matter everywhere. This insight revolutionized how we think about the cosmos. Before Newton, the heavens seemed separate from earthly affairs, following different rules in their celestial realm. Aristotle had taught that heavenly bodies moved in perfect circles because that was their natural motion, while earthly objects fell straight down because they sought their natural place. Newton swept away this artificial division with a single, elegant law. Every particle of matter attracts every other particle with a force proportional to their masses and inversely proportional to the square of the distance between them. The mathematics were beautiful in their simplicity, yet their implications were staggering. Newton's law of universal gravitation meant that a grain of sand on Earth exerted a tiny pull on Jupiter, and Jupiter pulled back. The most distant stars tugged gently on every atom in your body. The universe revealed itself as a vast web of gravitational connections, with every piece of matter influencing every other piece across the immense gulfs of space. Newton's gravity was a force of attraction, always pulling, never pushing. It reached across empty space instantaneously, somehow knowing exactly where every other piece of matter was located. This action at a distance puzzled even Newton himself. He wrote to a colleague that the idea of one body acting upon another through a vacuum without any medium was so great an absurdity that no one who had a competent faculty of thinking in philosophical matters could fall into it. Yet his equations worked perfectly, predicting the motions of planets with unprecedented accuracy. For over 2 centuries, Newton's vision reigned supreme. Astronomers used his equations to discover new planets by detecting their gravitational influence on known worlds. They calculated the masses of stars by watching how they pulled on their companions. They traced the orbits of comets and predicted their return with clockwork precision. Gravity became the cosmic accountant, keeping perfect books on the motion of everything from asteroids to galaxies. But as the 19th century gave way to the 20th, cracks began to appear in Newton's gravitational edifice. Mercury, the innermost planet, refused to behave exactly as Newton's equations predicted. Its orbit showed a tiny but persistent deviation, a slow rotation that accumulated over time. Astronomers searched desperately for an undiscovered planet that might explain the discrepancy, but found nothing. The answer came from an unexpected source, a young patent clerk in Switzerland named Albert Einstein. In 1915, Einstein published his theory of general relativity, which reimagined gravity not as a force, but as a curvature of space-time itself. Mass and energy, according to Einstein, warp the fabric of space and time, creating valleys and hills in the cosmic landscape. What we perceive as gravitational attraction is actually objects following the straightest possible paths through this curved geometry. Einstein's insight was radical beyond measure. Space and time, which Newton had considered absolute and unchanging, became dynamic and malleable. A massive star didn't pull on planets across empty space. Instead, it curved space-time so dramatically that planets had no choice but to orbit. The planets weren't being pulled, they were simply following the contours of reality itself. This new understanding of gravity solved Mercury's orbital puzzle immediately. The intense gravitational field near the Sun curved space-time so severely that it affected how orbits themselves evolved. But Einstein's theory predicted far more dramatic effects. It suggested that gravity could bend light, slow down time, and even create ripples in space-time itself that would propagate across the universe at light speed. Within a few years, observations confirmed Einstein's most startling predictions. During a solar eclipse in 1919, British astronomers measured starlight bending around the Sun exactly as general relativity predicted. Time dilation was detected in the gravitational redshift of light climbing out of gravitational wells. Gravity revealed itself as the master sculptor of space-time, shaping not just the paths of planets, but the very arena in which cosmic events unfold. This new understanding of gravity as curved space-time opened revolutionary possibilities for measuring cosmic time. If gravity shaped space and time themselves, then the gravitational history of the universe was literally written into the geometry of space-time. The expansion and contraction of the cosmos, the formation and evolution of galaxies, the birth and death of stars, all of these cosmic events left their signatures in the gravitational field that permeates all existence. Einstein's field equations, the mathematical heart of general relativity, revealed something even more profound. They described not just how matter curves space-time, but how that curvature evolves over time. The equations were dynamic, showing how the geometry of the universe changes as matter moves and energy flows. This meant that the entire cosmos had a history encoded in its gravitational structure. In Newton's universe, space was a fixed stage where gravitational drama played out. In Einstein's universe, space itself became an actor in the cosmic story. The universe could expand or contract. Its geometry could evolve, and the rate of that evolution depended on the total amount and distribution of matter and energy it contained. For the first time in human history, scientists had equations that could describe the temporal evolution of the entire cosmos. The implications were staggering. If the universe was expanding today, it must have been smaller yesterday and even smaller the day before that. Following this logic backwards through time led to an unavoidable conclusion. There must have been a moment when the expansion began, a cosmic birthday when space and time themselves came into existence. But Einstein himself initially resisted this conclusion. Like most thinkers of his era, he preferred an eternal, unchanging universe. When his own equations suggested the cosmos must be either expanding or contracting, he added a new term, the cosmological constant, to force them to describe a static universe. It was, he later called it, his greatest blunder. The cosmic implications of Einstein's gravity went far beyond planetary orbits and bending light. General relativity revealed that gravity operates as a cosmic clockmaker, its influence determining not just where objects go, but when events happen. In regions of strong gravitational fields, time itself runs slower, relative to regions where gravity is weaker. An astronaut orbiting close to a black hole would age more slowly than someone far from any massive object. This gravitational time dilation meant that the universe doesn't have a single, universal clock ticking at the same rate everywhere. Instead, time flows differently in different locations, depending on the local gravitational environment. The universe ages at different rates in different places, with cosmic time itself shaped by the distribution of matter and energy across space. Yet despite these local variations, the overall expansion of the universe provides something like a master timepiece. As space expands and matter spreads out, the average density of the universe decreases in a predictable way. This cosmic dilution happens at a rate determined by the fundamental properties of gravity and matter, creating a natural clock that measures the age of the universe as a whole. Einstein's revolution in understanding gravity transformed our concept of cosmic time from something that simply flows uniformly everywhere to something dynamic and measurable through gravitational effects. The curvature of space-time encodes information about the history and future evolution of the cosmos. Gravity became not just a force that moves objects around, but the fundamental mechanism by which the universe ages and evolves. This transformation set the stage for one of science's greatest discoveries: the realization that the universe is not static and eternal, but expanding and evolving. The key would come from combining Einstein's insights about gravity with careful observations of light from distant galaxies, revealing that the cosmos has been growing larger throughout its history, and allowing scientists to trace that growth backwards to find the moment when cosmic expansion began. Edwin Hubble peered through the eyepiece of the Mount Wilson Observatory's 100-inch telescope on a cool California night in 1923, not knowing he was about to overturn humanity's entire conception of the cosmos. What he saw through that lens would transform our understanding of space, time, and our place in existence itself. A single star, flickering in the Andromeda Nebula, was about to rewrite the story of the universe. That star was a Cepheid variable, a type of stellar lighthouse that pulses with mathematical regularity. Henrietta Swan Leavitt had discovered years earlier that these cosmic beacons follow a precise relationship between their pulsation period and their intrinsic brightness. The longer a Cepheid takes to complete its cycle of brightening and dimming, the more luminous it truly is. This relationship turns Cepheids into cosmic yardsticks allowing astronomers to measure distances across the galaxy and beyond. By comparing the apparent brightness of the Cepheid in Andromeda with its true luminosity calculated from its pulsation period, Hubble made a startling discovery. The Andromeda Nebula lay not within our own Milky Way galaxy, as most astronomers assumed, but at the almost incomprehensible distance of 2 million light-years away. Andromeda wasn't a nebula at all, but an entire galaxy like our own, containing hundreds of billions of stars. This revelation shattered the comfortable notion that our galaxy contained the entire universe. Suddenly, the cosmos expanded from a single island of stars to an ocean dotted with countless other galaxies, each containing more stars than humans had ever imagined existed. The universe revealed itself to be not just large, but almost unimaginably vast, filled with galaxies scattered across distances that made our solar system seem like a grain of sand on an endless beach. But Hubble's most revolutionary discovery was still to come. Working with his assistant Milton Humason throughout the 1920s, Hubble began measuring not just the distances to other galaxies, but also their motions relative to Earth. They accomplished this by analyzing the light from these distant star cities, looking for telltale shifts in the wavelengths of specific colors. Light behaves like sound in one crucial way. When the source moves toward or away from an observer, the wavelengths change. Just as the pitch of an ambulance siren rises as it approaches and falls as it recedes, light from an approaching object shifts toward bluer wavelengths, while light from a receding object shifts toward red. This Doppler effect provides a cosmic speedometer, revealing whether distant objects are moving toward or away from us. What Hubble and Humason discovered defied all expectations. Nearly every galaxy they observed showed redshift, meaning nearly every galaxy in the universe was racing away from Earth. The few exceptions were nearby galaxies like Andromeda, whose individual motions overwhelmed the larger cosmic pattern. But for galaxies beyond our immediate neighborhood, the message was clear and consistent. The universe was fleeing from us in all directions. Even more remarkable was the pattern Hubble discovered in this cosmic exodus. The farther away a galaxy was, the faster it appeared to be receding. Galaxies twice as distant moved away twice as fast. Galaxies 10 times farther away fled 10 times faster. This wasn't random motion, but a systematic relationship that seemed to govern the entire observable universe. In 1929, Hubble published his findings in a paper that would reshape cosmology forever. The relationship between distance and recession velocity, now known as Hubble's law, suggested something almost beyond comprehension. The universe itself was expanding. Space was stretching, carrying galaxies along like dots painted on an inflating balloon. This interpretation required a fundamental shift in thinking. Galaxies weren't moving through space away from Earth. Space itself was expanding between them. No galaxy was special or central. Each one would see all the others receding according to the same pattern. The expansion wasn't happening from some particular location, but everywhere simultaneously as the very fabric of space-time grew larger. The implications were staggering. If space was expanding now, it must have been smaller in the past. Following this logic backward through time led to an inescapable conclusion. There must have been a moment when all matter and energy in the universe occupied an infinitely small point. The universe had a beginning, a moment of creation that cosmologists would later call the Big Bang. Hubble's constant, the number describing how fast the universe expands, became the key to calculating the age of everything that exists. By measuring the current rate of expansion and working backward, scientists could estimate how long expansion had been occurring. The first crude calculations suggested the universe was about 2 billion years old, younger than some rocks on Earth. But subsequent refinements would push this age steadily older as measurement techniques improved. The expanding universe discovery connected directly to Einstein's general relativity in ways that amazed physicists. Einstein's field equations, when applied to the universe as a whole, naturally described an expanding or contracting cosmos. The Russian mathematician Alexander Friedmann had derived solutions to Einstein's equations in 1922 that showed space could expand, but most scientists, including Einstein himself, had dismissed these as mathematical curiosities with no physical meaning. Hubble's observations proved Friedmann right. The universe was indeed expanding, and Einstein's theory of gravity provided the perfect framework for understanding why. General relativity revealed that the expansion rate depended on the total density of matter and energy in the universe. More matter meant stronger gravitational attraction, which would slow the expansion. Less matter meant weaker gravity and faster expansion. This connection between gravity and cosmic expansion transformed our understanding of how the universe ages. The rate at which space expands determines how cosmic time unfolds. In Einstein's framework, gravity doesn't just bend space-time around individual stars and planets. It controls the evolution of space-time throughout the entire cosmos. The discovery that space itself expands also solved a puzzle that had bothered astronomers for decades. If the universe were infinite and unchanging, as most had assumed, then the night sky should blaze with the light of infinitely many stars. This paradox, known as Olbers' paradox after the German astronomer Heinrich Olbers, had suggested something was wrong with the eternal universe model. An expanding universe with a finite age provided the answer. We can only see light from stars within a finite distance because light from more distant objects hasn't had time to reach us yet. Hubble's discovery also revealed why the universe hadn't collapsed under its own gravity long ago. In Newton's theory, a universe filled with matter attracting itself should quickly contract into a single point. But in an expanding universe, the motion of expansion works against gravitational collapse, potentially allowing the cosmos to exist for billions of years without crushing itself. The expanding universe transformed time from a simple progression of moments into a dynamic quantity intimately connected to the geometry of space. As space expands, cosmic time advances, and the rate of that advancement depends on the gravitational properties of all the matter and energy the universe contains. Measuring the expansion rate became equivalent to measuring the universe's age. Yet Hubble's work raised as many questions as it answered. What caused the expansion to begin? Would it continue forever, or would gravity eventually halt the expansion and cause the universe to collapse? Did space expand at a constant rate, or had the expansion been accelerating or decelerating over cosmic history? Answering these questions would require understanding the expansion not just as it appears today, but as it has evolved over billions of years of cosmic history. Scientists would need to probe deeper into space and further back in time, using the most distant galaxies as fossil evidence of how the universe expanded when it was much younger. They would discover that the story of cosmic expansion is far more complex and surprising than Hubble could have imagined, with gravity playing an even more central role in determining the ultimate fate and age of everything that exists. But the story of cosmic expansion held deeper mysteries that would take decades to unravel. Hubble's initial measurements suggested an expansion rate that made the universe uncomfortably young, barely 2 billion years old according to the first calculations. This created what astronomers called the age problem. How could the universe be younger than the oldest stars it contained? Geologists had already determined that Earth itself was over 4 billion years old, making it seemingly impossible for the entire cosmos to be only half that age. The resolution would come through painstaking improvements in measurement techniques and a deeper understanding of the different types of stars used as cosmic distance markers. Walter Baades' work in the 1940s revealed that there were actually 2 different populations of Cepheid variables, each following slightly different period luminosity relationships. When this discovery was applied to recalibrate cosmic distances, the universe suddenly became much older and larger than Hubble had initially calculated. These revisions highlighted a crucial aspect of using expansion to measure cosmic age. The precision of the age calculation depends entirely on how accurately we can measure the current expansion rate. A small error in determining Hubble's constant translates into a large uncertainty in the universe's age. This drove astronomers to develop ever more sophisticated techniques for measuring cosmic distances, from analyzing the brightness of entire galaxies to studying the explosions of white dwarf stars called Type 1a supernovae. The challenge of cosmic distance measurement became one of astronomy's central preoccupations throughout the 20th century. Each new technique had to be carefully calibrated against closer objects whose distances were already known, creating what astronomers call the cosmic distance ladder. Parallax measurements of nearby stars formed the bottom rung, followed by a main sequence fitting for star clusters, then Cepheid variables for nearby galaxies, and finally various techniques for probing the most distant reaches of the observable universe. Every rung of this ladder introduced potential sources of error that could cascade through the entire cosmic age calculation. Systematic errors in measuring stellar parallaxes would throw off Cepheid calibrations, which would affect galaxy distance measurements, which would skew the calculation of Hubble's constant, and thus the universe's age. The interdependence of these measurements meant that determining cosmic age required not just theoretical understanding of expansion, but also extraordinary precision in observational astronomy. The expanding universe discovery also forced scientists to grapple with profound questions about the nature of space and time themselves. If space was expanding, what was it expanding into? The answer, according to general relativity, was that space wasn't expanding into anything. The universe contains all of space and time, so there's no external arena for it to expand into. Instead, the distances between objects simply increase as space-time itself stretches. This concept challenged human intuition in fundamental ways. We're accustomed to thinking of expansion as movement through space, like a balloon inflating in a room. But cosmic expansion is the stretching of space itself, creating more distance between objects without requiring them to move through any pre-existing medium. Galaxies aren't racing through space away from each other. They're being carried apart by the expansion of the space between them. The distinction matters crucially for understanding cosmic time. In Einstein's universe, space and time are unified into a four-dimensional space-time continuum. When space expands, it's not just the three spatial dimensions growing larger, but the entire space-time framework evolving according to the gravitational dynamics described by general relativity. The expansion of space and the flow of cosmic time are aspects of the same underlying phenomenon. This realization transformed how physicists thought about the relationship between gravity and time. In Newton's framework, gravity was a force acting within absolute space and time. In Einstein's framework, gravity is the curvature of space-time itself, and that curvature determines how both space and time evolve. The expansion of the universe became a gravitational phenomenon, with the rate of expansion determined by the total matter and energy content of the cosmos. Hubble's discovery also revealed that we live in a unique moment in cosmic history. The fact that we can observe distant galaxies and measure their recession velocities depends on light having enough time to travel from those galaxies to Earth, but not so much time that the expansion has carried them beyond our observational reach. In the very early universe, space was so dense and hot that light couldn't travel freely. In the far future, expansion may carry distant galaxies so far away that their light can never reach us. This observational window provides a finite span of cosmic time during which intelligent observers can discover the expanding universe and measure its age. the universe's expansion creates the very conditions that allow us to study cosmic expansion, a remarkable example of what some philosophers call the participatory universe principle. We can measure cosmic time precisely because we exist at a moment when such measurements are possible. The implications extended beyond astronomy into philosophy and theology. An expanding universe with a definite beginning challenged both scientific materialism, which had assumed an eternal cosmos, and religious doctrines that placed creation beyond scientific investigation. The Big Bang Theory, as it came to be called, suggested that space, time, matter, and energy all came into existence simultaneously at a specific moment in the finite past. This cosmic birthday raised profound questions about causation and existence. What caused the Big Bang? What, if anything, existed before it? Could science ever hope to understand the ultimate origin of everything that exists? These questions pushed the boundaries between physics and philosophy, between scientific investigation and metaphysical speculation. Yet despite these deep mysteries, Hubble's discovery provided something invaluable, a concrete, measurable pathway to determining the age of the universe. By carefully measuring how fast space is expanding today and understanding how that expansion rate has changed over cosmic history, scientists could work backward to find when expansion began. The universe revealed itself to have a birthday that could be calculated with increasing precision as observational techniques improved. The expanding universe became humanity's first glimpse of cosmic time in action. The realization that the entire cosmos has a history written in the very geometry of space-time itself. But reading that history accurately would require understanding not just that the universe expands, but exactly how the rate of expansion depends on the gravitational influence of all the matter and energy the cosmos contains. That understanding would come from mathematical insights that revealed how cosmic geometry encodes the passage of time itself. Alexander Friedmann sat in his study in Petrograd during the bitter winter of 1921, surrounded by the chaos of revolutionary Russia, yet focused on equations that would unlock the deepest secrets of cosmic time. While his country convulsed with political upheaval, this Russian mathematician was quietly deriving solutions to Einstein's field equations that would reveal how the entire universe ages and evolves. His work would prove that the cosmos itself has a life story written in the language of curved space-time. Friedmann approached Einstein's equations with fresh eyes, unencumbered by the assumption that the universe must be static and eternal. Where Einstein had added his cosmological constant to force the equations to describe an unchanging cosmos, Friedmann allowed them to speak for themselves. What they told him was revolutionary. The universe described by general relativity could not remain static. It must either expand or contract, growing larger or smaller as time advances. The mathematical framework Friedmann developed, now known as the Friedmann equations, revealed that cosmic expansion follows precise rules determined by the total amount and type of matter and energy the universe contains. These equations don't just describe how fast space expands today, but how that expansion rate changes over time in response to the gravitational pull of everything the cosmos contains. The first Friedmann equation relates the expansion rate of the universe to its energy density through a beautifully simple relationship. The square of the expansion rate equals 8 pi times Newton's gravitational constant times the energy density divided by 3 minus a curvature term that depends on the geometry of space itself. This elegant formula encapsulates one of the most profound insights in physics. The rate at which the universe ages depends on how much stuff it contains and how that stuff is distributed through space. But the Friedmann equations revealed something even more remarkable. Depending on the total density of matter and energy, the universe could have one of 3 possible geometries. each leading to a different cosmic fate and a different calculation of cosmic age. These three possibilities correspond to fundamental geometric concepts that mathematicians had explored for centuries: flat, curved inward, or curved outward space. In a flat universe, space follows the familiar geometry of Euclid. Parallel lines never meet, the angles of triangles add up to 180 degrees, and the circumference of a circle equals pi times its diameter. This geometry corresponds to a universe with exactly the critical density needed to balance expansion against gravitational collapse. A flat universe expands forever, but at an ever-decreasing rate, with the expansion approaching zero after infinite time. A closed universe curves inward like the surface of a sphere. In such a cosmos, parallel lines eventually converge. Triangle angles sum to more than 180 degrees, and traveling far enough in any direction brings you back to your starting point. This geometry arises when the universe contains more than the critical density of matter and energy. The extra gravitational pull eventually halts expansion and causes the universe to collapse back on itself in a cosmic crunch. An open universe curves outward like a saddle shape. Here, parallel lines diverge, triangle angles sum to less than 180 degrees, and space stretches infinitely in all directions. This geometry corresponds to a universe with less than critical density, where gravitational attraction is too weak to halt expansion. Such a universe expands forever at an accelerating rate. Each of these cosmic geometries leads to a different age calculation. The relationship between current expansion rate and total age depends critically on whether the universe is flat, closed, or open. In a closed universe dense with matter, strong gravitational attraction slows expansion so much that the cosmos reaches its current size relatively quickly, making it younger than a flat universe with the same current expansion rate. In an open universe with little matter, weak gravity allows rapid expansion, meaning the universe takes longer to reach its current size and is therefore older. The Friedmann equations also revealed how different types of matter and energy affect cosmic expansion in fundamentally different ways. Ordinary matter, the stuff that makes up stars and planets and people, behaves according to familiar rules. As the universe expands and matter spreads out, its density decreases proportionally to the volume of space. Double the size of the universe, and matter density drops by a factor of 8. But radiation, including light and other forms of electromagnetic energy, behaves differently during cosmic expansion. As space stretches, not only does radiation spread out to fill more volume, but the wavelengths of individual photons stretch as well. This double effect means radiation density decreases much faster than matter density as the universe expands. In the early universe, when space was compressed, radiation dominated the cosmic energy budget. As expansion proceeded, matter eventually took over as the primary component. This transition from radiation-dominated to matter-dominated expansion fundamentally changed how the universe aged. During the radiation era, the strong gravitational effects of concentrated energy caused rapid deceleration of expansion. The universe aged quickly during this phase, packing enormous changes in expansion rate into relatively short periods of time. As matter took over, expansion decelerated more gradually, allowing cosmic time to unfold at a steadier pace. The Friedmann equations predicted an even more exotic possibility: a form of energy that doesn't dilute as space expands. Einstein's cosmological constant represented one example of such energy, but physicists later realized that quantum effects could produce similar phenomena. This mysterious energy, eventually dubbed dark energy, would have the opposite effect of matter and radiation. Instead of slowing cosmic expansion through gravitational attraction, it would accelerate expansion by pushing space apart. If dark energy dominates the cosmic energy budget, the Friedmann equations predict a universe that expands at an ever-increasing rate. Such accelerated expansion would have profound implications for cosmic age calculations. A universe that spent its early history decelerating under the influence of matter but recently began accelerating due to dark energy would have a complex expansion history that requires careful analysis to determine its total age. The mathematical elegance of the Friedmann equations concealed their revolutionary implications for understanding cosmic time. These equations revealed that time itself is not separate from the cosmic expansion, but intimately connected to it. The rate at which cosmic time advances depends on the gravitational dynamics of space-time expansion. Measuring the universe's age becomes equivalent to solving the Friedmann equations with the correct values for cosmic density and geometry. This connection between cosmic expansion and the flow of time also illuminated why the universe's age can be determined from astronomical observations. By measuring how fast space expands today and determining what types of matter and energy fill the cosmos, scientists can use the Friedmann equations to trace expansion backward through time to the moment when it began. The cosmic expansion rate becomes a direct measure of how old the universe is. The Friedmann equations also reveal deep connections between cosmic geometry and cosmic time. In Einstein's universe, space and time form a unified four-dimensional continuum, and the curvature of this space-time determines both the geometry of space and the evolution of cosmic expansion. A universe with spherical spatial geometry corresponds to space-time that curves back on itself, leading to eventual collapse. A universe with hyperbolic spatial geometry corresponds to space-time that curves away from itself, leading to eternal expansion. This geometric interpretation of cosmic evolution provided powerful new ways to think about measuring the universe's age. Instead of simply timing how long expansion has been occurring, scientists could determine cosmic age by measuring the curvature of space-time itself. The geometry of the universe encodes its entire history, including its age, in mathematical relationships that can be extracted through careful observation. But applying the Friedmann equations to determine cosmic age required knowing the values of several key parameters: the current expansion rate, the total density of matter and energy, and the relative amounts of different types of cosmic components. Each of these quantities had to be measured through astronomical observations, and small errors in any measurement would propagate through the age calculation. The challenge of determining these cosmic parameters drove much of 20th century cosmology. Astronomers developed increasingly sophisticated techniques for measuring the expansion rate through observations of distant supernovae, the matter density through studies of galaxy clustering, and the radiation density through detection of the cosmic microwave background. Each new measurement refined the cosmic age calculation and tested the predictions of the Friedmann equations. The equations also predicted that cosmic expansion should leave observable signatures in the large-scale structure of the universe. Tiny density fluctuations in the early cosmos would grow under gravitational attraction, but their growth rate would depend on the expansion history determined by the Friedmann equations. By studying how matter clumped together to form galaxies and galaxy clusters, astronomers could test whether the observed cosmic structures matched the predictions of different expansion models. Perhaps most remarkably, the Friedmann equations revealed that the universe's age is not just a single number, but depends on the cosmic location where it's measured. In regions where matter is more densely concentrated, stronger gravitational fields cause time to run more slowly, relative to regions where matter is more sparse. The universe ages at different rates in different places, with the overall cosmic age representing an average over all locations. This insight connected cosmic age measurement to one of Einstein's most profound discoveries: gravitational time dilation. Just as clocks run slower in stronger gravitational fields, the universe itself ages more slowly in regions where matter and energy are more concentrated. The cosmic age calculated from expansion observations represents the time that would be measured by an observer moving with the average expansion of space, removed from local gravitational effects. The Friedmann equations transformed cosmic age from a philosophical question into a precise mathematical problem. By encoding the relationship between cosmic expansion, matter density, and space-time geometry, these equations provided the theoretical framework needed to convert astronomical observations into age measurements. The universe revealed itself to be not just expanding, but expanding according to mathematical laws that connect its geometry, its contents, and its age in fundamental ways. Two fundamentally different approaches emerged for measuring the age of the universe, each offering unique insights into cosmic time while serving as crucial checks on the other. The first path followed light itself, tracing electromagnetic radiation from the most distant corners of the cosmos to reveal how the universe looked when it was young. The second path followed gravity, studying how gravitational attraction has shaped the growth of cosmic structure over billions of years. Together, these complementary approaches would provide the most precise determination of cosmic age ever achieved. The light-based approach capitalizes on a remarkable property of astronomical observation. Looking out into space means looking back in time. When we observe a galaxy 1 billion light-years away, we see it as it existed 1 billion years ago, when the light now reaching us first began its journey across the cosmos. The most distant observable objects show us the universe when it was a small fraction of its current age, providing direct glimpses into cosmic infancy. The crown jewel of light-based cosmic dating came from the discovery of the cosmic microwave background radiation, a faint glow of ancient light that fills all of space. This radiation represents the afterglow of the Big Bang itself, released when the universe first became transparent to light, approximately 3 billion years ago, 180,000 years after its beginning. Unlike starlight from distant galaxies, which shows us the universe at various stages of its development, the cosmic microwave background provides a snapshot of the cosmos at a single, precisely determined moment in its early history. The properties of this ancient light encode extraordinary information about cosmic age. The temperature of the radiation today, measured at approximately 2.7 degrees above absolute zero, combined with our understanding of how the universe has expanded and cooled since the radiation was released, allows scientists to calculate exactly how much time has elapsed since that moment of cosmic transparency. The cosmic microwave background thus serves as a fossil record of the universe's youth, preserving details about cosmic expansion that can be translated directly into age measurements. But the cosmic microwave background reveals more than just the universe's temperature in its youth. Tiny variations in the radiation's intensity across different directions in the sky, typically differing by only a few parts in 100,000, map out the distribution of matter and energy when the universe was still a cosmic infant. These variations represent the seeds from which all large-scale cosmic structure eventually grew, and their precise pattern depends sensitively on the total age of the universe. The analysis of these temperature variations requires extraordinary precision. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck mission have mapped the cosmic microwave background with increasing detail, revealing subtle patterns that encode the fundamental parameters governing cosmic expansion. By comparing the observed patterns with theoretical predictions from different cosmological models, scientists can determine not just the age of the universe, but also its geometry, composition, and expansion history. Stellar evolution provides another powerful light-based approach to cosmic dating. Stars age according to well-understood physical processes, burning nuclear fuel at rates determined by their mass and composition. The most massive stars live fast and die young, exhausting their fuel in millions of years. Medium-sized stars like our Sun burn more slowly, shining for billions of years. The smallest stars are so miserly with their fuel that they can shine for trillions of years. This relationship between stellar mass and lifetime creates cosmic chronometers. By studying the oldest star clusters and determining which types of stars have already died, while others continue to shine, astronomers can calculate how long those clusters have existed. The oldest known star clusters provide lower limits on the universe's age, since the cosmos must be at least as old as the ancient stars it contains. Globular clusters, dense collections of hundreds of thousands of stars that orbit the halos of galaxies, prove particularly valuable for this type of age determination. These clusters formed very early in cosmic history and contain some of the oldest stars in the universe. By carefully analyzing the colors and brightnesses of stars in globular clusters, astronomers can determine which stars are still burning hydrogen in their cores and which have evolved to later stages of stellar life. The boundary between these two populations, known as the main sequence turn-off point, provides a direct measure of cluster age. Stars just massive enough to have exhausted their core hydrogen fuel define this boundary, and the mass of these stars, combined with theoretical calculations of stellar evolution rates, yields the time since the cluster formed. The oldest globular clusters consistently indicate ages of approximately 12 to 13 billion years, providing strong constraints on cosmic age. White dwarf stars offer yet another light-based cosmic clock. These stellar remnants, the cooling cores of stars that have exhausted their nuclear fuel, fade predictably over time according to well-understood physics. By measuring the temperatures and colors of the coolest white dwarfs in our galaxy, astronomers can determine how long they have been cooling. The coolest white dwarfs place lower limits on cosmic age, since the universe must be old enough for stars to have lived their entire lives and cooled to their observed temperatures. Supernovae, the explosive deaths of certain types of stars, provide cosmic lighthouses that can be seen across billions of light years. Type Ia supernovae, which occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass and explode, serve as remarkably precise standard candles. These explosions produce very similar peak brightnesses, allowing astronomers to use them as cosmic distance markers. By measuring both the distances and recession velocities of supernova at various cosmic distances, astronomers can map out how the expansion rate of the universe has changed over time. This expansion history, when fed into the Friedmann equations, yields precise determinations of cosmic age. The Supernova Cosmology Project and the HISES Supernova Search Team use this technique to make one of the most surprising discoveries in modern cosmology. The expansion of the universe is accelerating, driven by mysterious, dark energy. While light-based methods probe cosmic time through electromagnetic radiation, gravity-based approaches study how gravitational attraction has shaped the growth of cosmic structure over billions of years. These methods capitalize on the fact that gravity leaves distinctive fingerprints in the distribution of matter throughout the universe, and the strength and pattern of these fingerprints depend on how long gravity has been at work. The large-scale structure of the universe, the cosmic web of galaxies and galaxy clusters connected by filaments of dark matter, represents the cumulative result of billions of years of gravitational evolution. Tiny density fluctuations in the early universe grew under their own gravitational attraction, eventually forming the galaxies and clusters we observe today. The rate of this structure formation depends on the cosmic expansion history, the total amount of matter in the universe, and the strength of gravitational attraction itself. By surveying millions of galaxies and measuring how they cluster together on different scales, astronomers can determine the statistical properties of cosmic structure. These measurements reveal how strongly matter clumps together, how the clustering strength varies with distance scale, and how the clustering pattern has evolved over cosmic time. All of these properties depend sensitively on the age of the universe and the expansion history it has experienced. Computer simulations of cosmic evolution provide the theoretical framework for interpreting these observations. By modeling how matter moves under gravitational attraction in an expanding universe, scientists can predict what patterns of clustering should emerge for different cosmic ages and expansion histories. Comparing these predictions with observed galaxy distributions allows precise determinations of cosmic parameters, including the universe's age. Galaxy formation itself provides another gravity-based cosmic clock. The process by which gas collapses under gravitational attraction to form stars and galaxies takes time that depends on the cosmic environment and expansion history. By studying galaxies at different distances and thus different cosmic epochs, astronomers can trace how galaxy properties have evolved and determine how long various stages of galaxy formation require. The most distant galaxies, observed when the universe was only a few 100 million years old, appear smaller, more irregular, and more actively star-forming than nearby galaxies. This evolution reflects the ongoing process of galaxy assembly through gravitational mergers and accretion. The timescales required for these processes, combined with the observed properties of galaxies at different cosmic epochs, constrain the age of the universe and the expansion history it has experienced. Gravitational lensing provides yet another gravity-based approach to cosmic dating. When light from distant galaxies passes through the gravitational field of intervening matter, it bends and distorts in ways that reveal the distribution of both visible and dark matter. Strong lensing creates multiple images of background galaxies, while weak lensing causes subtle distortions in galaxy shapes that can be detected statistically across large surveys. The strength and pattern of gravitational lensing effects depend on the cosmic expansion history and the growth rate of cosmic structure. By measuring lensing distortions for galaxies at various distances, astronomers can map how the universe's matter distribution has evolved over time. This evolution, when compared with theoretical predictions, provides independent constraints on cosmic age and expansion history. Perhaps most remarkably, these light-based and gravity-based approaches generally agree on the age of the universe to within the uncertainties of the measurements. The cosmic microwave background indicates an age of approximately 13.8 billion years. Stellar evolution studies suggest ages in the range of 12 to 14 billion years. Supernova observations, when combined with other measurements, yield similar values. Galaxy clustering and gravitational lensing studies provide consistent results. This convergence of independent measurement techniques represents one of the great triumphs of modern cosmology. The fact that methods based on fundamentally different physics, electromagnetic radiation versus gravitational dynamics, yield consistent answers, provides strong confidence in our understanding of cosmic age. No single measurement technique is perfect, but the agreement among multiple independent approaches makes the age determination remarkably robust. Yet subtle discrepancies between different methods continue to drive cutting-edge research. The Hubble tension, a small but persistent disagreement between cosmic age measurements based on local observations versus global cosmic background measurements, suggests that our understanding of cosmic expansion may still be incomplete. Resolving these tensions may require new physics or more precise measurements, pushing the boundaries of cosmic age determination to ever greater accuracy. The combination of light-based and gravity-based cosmic dating techniques has transformed our understanding of the universe from a timeless cosmos to a dynamic system with a well-determined age and expansion history. Together, these approaches reveal that we live in a universe that began approximately 13.8 billion years ago and has been expanding and evolving according to the laws of gravity and quantum physics ever since. In 1965, two radio engineers at Bell Laboratories in New Jersey made an accidental discovery that would revolutionize our understanding of cosmic time. Arno Penzias and Robert Wilson were trying to eliminate an annoying hiss from their sensitive microwave antenna, a persistent background noise that seemed to come from everywhere in the sky. No matter which direction they pointed their instrument, no matter what time of day or night they observed, the mysterious signal remained constant. What they had stumbled upon was the afterglow of creation itself, a fossil record of the universe's infancy that would become the most precise cosmic clock ever discovered. This cosmic microwave background radiation represents light that has been traveling through space for over 13 billion years, released when the universe first became transparent in its early history. During the first few 100,000 years after the Big Bang, the cosmos was so hot and dense that free electrons scattered photons constantly, making space opaque like the interior of a star. But as expansion cooled the universe below about 3,000 degrees, electrons combined with protons to form neutral hydrogen atoms in an event cosmologists call recombination. Suddenly, photons could travel freely through space for the first time. The universe became transparent, releasing a brilliant flash of light that filled all of space. This light has been cooling and stretching as space expands ever since, its wavelength increasing from visible light to infrared to the microwave radiation we detect today. The cosmic microwave background is literally the oldest light in the universe, a direct observation of conditions when the cosmos was less than 1% of its current age. The remarkable uniformity of this ancient light initially puzzled scientists. In every direction astronomers looked, the temperature of the cosmic microwave background measured almost exactly 2.725 degrees above absolute zero. This extraordinary uniformity suggested that the early universe was incredibly smooth, with matter and energy distributed almost perfectly evenly throughout space. But this smoothness created a paradox. If the early universe was so uniform, how did the lumpy structures we see today, galaxies and clusters separated by vast voids, ever form? The answer came from increasingly sensitive measurements that revealed tiny variations in the cosmic microwave background temperature, typically differing by only about 10 to 20 parts per million across different regions of the sky. These minuscule fluctuations represent density variations in the early universe, regions that were slightly denser or less dense than average when the background radiation was released. Though tiny, these variations provided the gravitational seeds from which all cosmic structure eventually grew. The pattern of these temperature fluctuations encodes an extraordinary amount of information about the universe's age, composition, and geometry. The fluctuations aren't random, but follow specific statistical patterns that depend on the physical processes operating in the early cosmos. Sound waves traveling through the primordial plasma before recombination created a series of peaks and valleys in the density distribution, and these acoustic oscillations left their signature imprinted in the cosmic microwave background. These baryon acoustic oscillations, as physicists call them, represent sound waves frozen in time. Before recombination, pressure from hot photons could support sound waves traveling through the cosmic plasma at about half the speed of light. These waves originated from quantum fluctuations in the very early universe and had been propagating for hundreds of thousands of years when recombination suddenly stopped their motion. The wavelengths of these frozen sound waves, visible as patterns in the cosmic microwave background, provide a standard ruler for measuring cosmic distances and determining the universe's geometry. The size of the largest acoustic oscillation feature, corresponding to the distance sound could travel in the time between the Big Bang and recombination, depends critically on the age of the universe at recombination. If the universe were older at that time, sound waves would have had longer to propagate, and the characteristic scale would be larger. If it were younger, the scale would be smaller. By measuring this characteristic scale and comparing it with theoretical predictions, scientists can determine precisely how old the universe was when the cosmic microwave background was released. But the cosmic microwave background encodes far more information than just the age at recombination. The detailed pattern of temperature fluctuations depends on the total density of matter in the universe, the relative amounts of ordinary and dark matter, the curvature of space, and the expansion rate both before and after recombination. Each of these parameters leaves distinctive signatures in the fluctuation pattern, allowing scientists to determine all the fundamental cosmic parameters simultaneously from a single comprehensive analysis. The Cosmic Background Explorer satellite, launched in 1989, provided the first detailed map of cosmic microwave background fluctuations and confirmed that their pattern matched the predictions of Big Bang cosmology with remarkable precision. The satellite's measurements earned John Mather and George Smoot the Nobel Prize in Physics in 2006 for their discovery of the blackbody form and anisotropy of the cosmic microwave background radiation. But COBE's angular resolution, while revolutionary, could only detect fluctuations on relatively large scales. More detailed information required higher resolution observations that could map smaller scale variations in the background radiation. Ground-based experiments like Boomerang and Maxima, using balloon-borne telescopes flown above most of Earth's atmosphere, began to reveal the fine structure of cosmic microwave background fluctuations. These higher resolution measurements revealed something remarkable. The fluctuation pattern showed clear evidence of the acoustic oscillations predicted by Big Bang theory. The power spectrum of fluctuations, showing how much variation exists on different angular scales, displayed a series of peaks corresponding to sound waves of different wavelengths that were propagating when recombination occurred. The location, height, and spacing of these acoustic peaks provided exquisitely sensitive tests of cosmological models. The Wilkinson Microwave Anisotropy Probe, launched in 2001, revolutionized cosmic microwave background science by mapping the entire sky with unprecedented precision and sensitivity. Operating from a gravitationally stable point in space 4 times farther from Earth than the Moon, WMAPI could observe the cosmic microwave background without interference from Earth's atmosphere or thermal emission. WMAP's 9-year survey produced temperature maps precise enough to measure fluctuations at the level of a few millionths of a degree. These measurements revealed the acoustic oscillation pattern in exquisite detail, with multiple peaks and valleys clearly visible in the power spectrum. The data strongly favored a flat universe dominated by dark matter and dark energy, with ordinary matter comprising only about 5% of the total cosmic energy budget. Most importantly, for cosmic age determination, WMAP's measurements of the acoustic oscillation scale provided a precise measurement of the universe's age. 13.77 billion years, with an uncertainty of only about 60 million years. This represented the most accurate age determination ever achieved, precise to better than 0.5%. The cosmic microwave background had become humanity's most reliable cosmic clock. The European Space Agency's Planck mission, operational from 2009 to 2013, pushed cosmic microwave background measurements to even greater precision. With higher sensitivity and better angular resolution than WMAP, Planck mapped temperature fluctuations across the entire sky with unprecedented detail. The mission also measured polarization patterns in the cosmic microwave background, providing additional information about conditions in the early universe. Planck's final results refined the cosmic age measurement to 13.797 billion years, with an uncertainty of only about 23 million years. This extraordinary precision, better than 2 parts in 1,000, represents one of the most accurate measurements in all of science. The consistency between Planck's results and earlier WMAP measurements provided strong confirmation that scientists had correctly understood the physics of the cosmic microwave background. The polarization measurements from Planck revealed additional layers of information encoded in the ancient light. Photons can be polarized in different directions, and the pattern of polarization across the sky reflects how the cosmic plasma was moving when recombination occurred. These motions were driven by gravitational effects, providing another way to study how gravity shaped the early universe and influenced cosmic evolution. The cosmic microwave background also provides a unique window into inflation, a period of exponential expansion that many cosmologists believe occurred during the universe's first fraction of a second. Quantum fluctuations during inflation would have been stretched to cosmic scales, providing the initial seeds for all cosmic structure. The nearly scale-invariant pattern of fluctuations observed in the cosmic microwave background matches the predictions of inflationary models remarkably well. If gravitational waves were produced during inflation, they would leave a distinctive signature in the polarization pattern of the cosmic microwave background. Several experiments, including ground-based telescopes in Antarctica and planned space missions, are searching for this primordial gravitational wave signal. Detection of inflation-generated gravitational waves would provide direct evidence for the inflationary epoch and additional constraints on cosmic age and evolution. The cosmic microwave background measurements have also revealed subtle deviations from perfect uniformity that weren't predicted by the simplest cosmological models. Large-scale asymmetries and correlations in the fluctuation pattern suggest that the universe may be more complex than initially thought. Understanding these anomalies may require modifications to standard cosmology or could point toward new physics operating in the early universe. Despite these mysteries, the cosmic microwave background provides the most comprehensive and precise measurement of cosmic age currently available. Its ancient light carries information from a time when the universe was simpler and more uniform than today, allowing clear determination of fundamental cosmic parameters. The acoustic oscillation patterns frozen into the radiation provide standard rulers that work independently of the cosmic distance ladder, giving cosmic age measurements that don't depend on uncertain calibrations of stellar distances. The precision of cosmic microwave background age measurements has made them the gold standard for cosmology, but this precision has also highlighted small discrepancies with other measurement techniques. The Hubble tension, a disagreement between cosmic microwave background measurements and local measurements of the expansion rate, suggests that either systematic errors affect one or both techniques, or that new physics operates in ways that aren't captured by current cosmological models. Resolving the Hubble tension has become one of the most important challenges in modern cosmology. If the discrepancy is real, rather than due to measurement errors, it could point toward new physics, such as evolving dark energy, additional types of neutrinos, or modifications to general relativity. Alternatively, it might indicate that the universe's expansion history is more complex than current models assume. The cosmic microwave background represents more than just ancient light. It embodies the echo of gravity's influence on the early universe. The tiny fluctuations we observe today grew from quantum mechanical variations in the primordial cosmos, amplified by gravitational effects during inflation and modified by acoustic oscillations in the pre-recombination plasma. Every feature in the cosmic microwave background temperature map reflects gravitational processes operating when the universe was young. This connection between gravity and the cosmic microwave background makes the ancient radiation particularly valuable for cosmic age determination. Unlike measurements that depend on understanding stellar evolution or cosmic distance scales, cosmic microwave background age determinations rely primarily on well-tested physics of gravity, thermodynamics, and atomic structure. The robustness of the underlying physics gives high confidence in the resulting age measurements. The cosmic microwave background thus serves as both a fossil record of cosmic youth and a gravitational fingerprint of early universe physics. Its precise temperature and polarization patterns encode the age of the universe with extraordinary accuracy, making it humanity's most reliable cosmic clock and our best window into the gravitational processes that shaped cosmic evolution from its earliest moments. On September 14th, 2015, at 5:51 in the morning Eastern Daylight Time, two identical detectors separated by 3,000 kilometers simultaneously recorded the most faint signal ever measured by human instruments. For 0.2 of a second, laser beams in Louisiana and Washington state detected changes in distance smaller than 1/10,000th the width of a proton. This infinitesimal distortion of space-time itself marked humanity's first direct detection of gravitational waves, ripples in the fabric of reality that had traveled for over 1 billion years to reach Earth. The signal, later designated GW150914, originated from the collision and merger of two black holes, each about 30 times more massive than our Sun. In the final moments before merger, these gravitational titans spiraled around each other at nearly half the speed of light, converting the mass of 3 entire suns into pure gravitational wave energy in less time than it takes to blink an eye. The violence of this cosmic catastrophe sent ripples through space-time that stretched and compressed every meter of space by amounts smaller than the nucleus of an atom. Einstein had predicted the existence of gravitational waves a century earlier as a natural consequence of general relativity. If accelerating electric charges produce electromagnetic waves, he reasoned, then accelerating masses should produce gravitational waves. But Einstein himself doubted these waves could ever be detected. The distortions they cause are so incredibly small that he thought no conceivable instrument could measure them. He was nearly right. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, succeeded where Einstein thought failure was inevitable through a combination of revolutionary engineering and exquisite precision. Each LIGO detector consists of two 4-kilometer-long arms arranged in an L shape, with a laser light bouncing back and forth between mirrors at the ends of each arm. When a gravitational wave passes through the detector, it stretches space in one direction while compressing it in the perpendicular direction, causing tiny changes in the time it takes light to travel down each arm. These changes are so small that LIGO must isolate its mirrors from every conceivable source of vibration. The mirrors hang from multi-layer pendulum systems that filter out ground motion. The entire apparatus operates in ultra-high vacuum to eliminate pressure fluctuations from affecting the laser beams. Active feedback systems compensate for thermal expansion, seismic noise, and even the gravitational effects of clouds passing overhead. The result is perhaps the most sensitive measuring device ever constructed, capable of detecting length changes smaller than the width of atomic nuclei across distances of several kilometers. But LIGO's achievement goes far beyond technological triumph. Gravitational wave detections have opened an entirely new window for studying cosmic evolution and measuring cosmic time. Unlike electromagnetic radiation, which can be absorbed, scattered, or blocked by intervening matter, gravitational waves travel unimpeded through the universe. They carry pristine information about the most violent events in cosmic history, providing direct access to phenomena that remain hidden from conventional telescopes. The black hole mergers detected by LIGO offer a new type of cosmic standard candle for measuring distances across the universe. When two black holes spiral together, the gravitational waves they emit follow precise mathematical patterns determined by Einstein's equations. The amplitude of these waves depends on the masses of the merging black holes and their distance from Earth, while the frequency evolution depends only on the masses and other intrinsic properties. By analyzing the gravitational wave signal, scientists can determine both the masses of the merging black holes and the total energy radiated in gravitational waves. This information, combined with the observed amplitude of the waves when they reach Earth, allows a direct calculation of the distance to the merger event. Unlike conventional astronomical distance measurements, this technique doesn't depend on calibrating a cosmic distance ladder or understanding the complex physics of stellar evolution. Gravitational wave sources that can be localized to specific galaxies or galaxy clusters provide what astronomers call standard sirens, analogous to the standard candles used in conventional cosmology, but based on gravity rather than light. If the host galaxy of a gravitational wave source can be identified through electromagnetic observations, astronomers can measure both the distance to the galaxy from gravitational waves and its recession velocity from optical spectroscopy. This combination of gravitational wave distance and optical recession velocity provides an independent measurement of the cosmic expansion rate, potentially helping to resolve the Hubble tension that has emerged between different cosmic age determination methods. Standard sirens offer a completely independent check on cosmic expansion measurements that doesn't rely on the cosmic distance ladder or cosmic microwave background observations. The first such standard siren measurement came from GW170817, a gravitational wave source detected on August 17, 2017. Unlike previous detections from black hole mergers, this signal originated from the collision of two neutron stars, extremely dense stellar remnants that can produce electromagnetic radiation in addition to gravitational waves. Within seconds of the gravitational wave detection, telescopes around the world began searching for the electromagnetic counterpart to this cosmic collision. The search succeeded spectacularly. Astronomers identified the host galaxy NGC 4993 in the constellation Hydra, located about 130 million light-years from Earth. The optical and infrared emissions from the neutron star merger, dubbed a kilonova for its brilliance, provided confirmation that gravitational waves and electromagnetic radiation had indeed originated from the same cosmic event. By combining the distance measurement from gravitational waves with the recession velocity measured from the host galaxy's spectrum, astronomers obtained an independent determination of the Hubble constant. This first standard siren measurement yielded a value consistent with both cosmic microwave background and local measurements, though with relatively large uncertainties due to the difficulty of precisely localizing gravitational wave sources. Future gravitational wave detections promise to refine cosmic expansion measurements and provide increasingly precise tests of cosmological models. As LIGO's sensitivity improves and additional detectors come online around the world, the number of detectable gravitational wave sources will increase dramatically. The European Virgo detector has already joined LIGO in forming a global network, and the Japanese Kagura detector is beginning operations to create an even more sensitive worldwide array. These ground-based detectors can observe gravitational waves with frequencies between roughly 10 and several thousand cycles per second, corresponding to the final moments when compact objects spiral together and merge. But gravitational waves span an enormous range of frequencies, and different frequency ranges require different detection techniques. Just as astronomers use radio telescopes, optical telescopes, and X-ray satellites to observe different types of electromagnetic radiation, gravitational wave astronomy requires multiple types of detectors to observe different frequency ranges. Space-based gravitational wave detectors will access much lower frequencies than ground-based instruments, observing waves with periods ranging from seconds to hours. The European Space Agency's LISA mission, planned for launch in the 2030s, will use 3 spacecraft separated by millions of kilometers to detect gravitational waves from massive black hole mergers, white dwarf binaries in our galaxy, and potentially exotic sources from the early universe. LISA's observations will complement ground-based detectors by accessing gravitational wave sources that evolve over much longer timescales. While LIGO observes the final moments of black hole mergers, LISA will track the gradual in-spiral of massive black holes over months or years before they finally merge. This extended observation period will allow extremely precise measurements of source properties and distances, potentially making space-based standard sirens even more accurate tools for cosmology. Pulsar timing arrays represent another approach to gravitational wave detection that accesses even lower frequencies. Pulsars are rotating neutron stars that emit regular pulses of radio waves with clockwork precision. By monitoring the arrival times of these pulses at Earth over many years, astronomers can detect the tiny changes in arrival time caused by gravitational waves stretching and compressing the space between pulsars and Earth. The gravitational waves detectable by pulsar timing have frequencies corresponding to periods of years to decades, produced by supermassive black hole binaries in distant galaxies, or potentially by cosmic processes in the early universe. These ultra-low frequency gravitational waves carry information about cosmic evolution over the longest timescales, providing yet another window into the gravitational processes that shape cosmic history. Perhaps most exciting for cosmic age determination is the possibility that future gravitational wave detectors might observe primordial gravitational waves from the early universe itself. Just as the cosmic microwave background preserves a snapshot of electromagnetic radiation from recombination, primordial gravitational waves would preserve information about gravitational processes operating when the universe was much younger than recombination. Inflation, the period of exponential expansion thought to have occurred during the universe's first fraction of a second, would have generated gravitational waves that stretched to cosmic scales. These primordial gravitational waves would carry information about the earliest moments of cosmic evolution, potentially providing direct observational access to physics, operating when the universe was less than a billionth of a billionth of a billionth of a second old. Detection of primordial gravitational waves would revolutionize our understanding of cosmic time by providing observational access to epochs far earlier than any electromagnetic radiation can reach. The cosmic microwave background shows us the universe when it was about 380,000 years old. Primordial gravitational waves could show us the universe when it was younger than a trillionth of a second old, opening an observational window into the very beginning of cosmic time. Current upper limits on primordial gravitational waves, derived from cosmic microwave background observations, already provide constraints on inflationary models and early universe physics. Direct detection of these waves would test fundamental theories about the origin of the universe and provide precise measurements of cosmic parameters during the earliest moments of cosmic evolution. The gravitational wave spectrum also encodes information about cosmic expansion history in ways that complement electromagnetic observations. As gravitational waves travel through expanding space, their wavelengths stretch just like electromagnetic radiation, causing their frequencies to redshift. The amount of this gravitational redshift depends on the expansion history the waves experienced during their journey to Earth. By comparing the gravitational wave frequency observed at Earth with the frequency emitted by the source, astronomers can determine the cumulative expansion that occurred during the wave's travel time. For sources at different distances, this provides a map of how cosmic expansion has evolved over time, potentially revealing subtle deviations from the standard cosmological model. Advanced gravitational wave detectors may also be sensitive to modifications of gravity itself. Alternative theories of gravity predict different patterns of gravitational wave emission and propagation compared to Einstein's general relativity. By testing whether observed gravitational waves match Einstein's predictions with high precision, astronomers can verify that general relativity correctly describes gravity on cosmic scales and over cosmic time. The speed of gravitational waves provides another fundamental test of gravitational physics. Einstein's theory predicts that gravitational waves travel at exactly the speed of light. but alternative theories allow for different propagation speeds. The joint observation of GW170817 and its electromagnetic counterpart confirmed that gravitational waves and light arrived at Earth within seconds of each other after traveling for 130 million years, providing the most precise test ever of whether gravity and electromagnetism propagate at the same speed. Future gravitational wave observations will test Einstein's theory with even greater precision, potentially revealing deviations that could point toward new physics or modifications to general relativity. Such discoveries would have profound implications for understanding cosmic evolution and measuring cosmic time, since the equations governing cosmic expansion are derived from Einstein's theory of gravity. Gravitational wave astronomy has transformed from theoretical prediction to observational reality in just a few years, opening new perspectives on cosmic time measurement and cosmic evolution. These ripples in space-time itself provide the most direct possible observations of gravitational physics in action, carrying information about the universe's most violent events and potentially its earliest moments. As gravitational wave detectors become more sensitive and more numerous, they promise to provide increasingly precise and independent measurements of cosmic age, helping to resolve current tensions in cosmology and potentially revealing new physics that governs the evolution of space and time themselves. The universe appears to have developed a split personality, at least according to our most precise measurements of its age and expansion rate. Two completely independent methods for determining how fast the cosmos is expanding today yield results that disagree by just enough to make cosmologists profoundly uncomfortable. This disagreement, known as the Hubble tension, suggests either that systematic errors plague our most careful measurements, or that our fundamental understanding of cosmic evolution contains crucial missing pieces. The cosmic microwave background observations from the Planck satellite yield a Hubble constant of approximately 67 kilometers per second per megaparsec, with an uncertainty of less than 1%. This measurement emerges from analyzing the acoustic oscillation patterns frozen into the ancient light of recombination, combined with our best theoretical understanding of how the universe has evolved since that time. The resulting age calculation places the universe at 13.8 billion years old, give or take a few tens of millions of years. But when astronomers measure the expansion rate using local distance indicators, they consistently obtain higher values. The most precise local measurements, led by teams using the Hubble Space Telescope to observe Cepheid, variable stars, and type Ia supernovae, yield a Hubble constant of approximately 74 kilometers per second per megaparsec. This 7 kilometer per second difference might seem small, but it represents a discrepancy of about 10%, far larger than the uncertainties claimed by either measurement technique. This disagreement translates directly into conflicting age determinations. If the local expansion rate measurements are correct, the universe is approximately 12.8 billion years old, nearly 1 billion years younger than the cosmic microwave background indicates. This billion-year discrepancy represents one of the most significant puzzles in modern cosmology, challenging our understanding of cosmic evolution at its most fundamental level. The tension emerged gradually as measurement precision improved throughout the early 21st century. Initial measurements from both local and cosmic microwave background techniques had uncertainties large enough to accommodate disagreement, but as systematic errors were identified and eliminated, the measurements became more precise while remaining stubbornly inconsistent. The more carefully astronomers measured, the more persistent the disagreement became. Adam Riess, who shared the Nobel Prize for the discovery of cosmic acceleration, has led much of the local measurement effort using Cepheid variables as primary distance indicators. These pulsating stars follow a precise relationship between their pulsation period and intrinsic brightness, allowing astronomers to determine their distances by comparing apparent and absolute magnitudes. By observing Cepheids in galaxies that also host Type Ia supernovae, Rees and his collaborators have calibrated these stellar explosions as secondary distance indicators for probing much greater cosmic distances. The Hubble Space Telescope has been crucial for these measurements, providing the resolution needed to identify individual Cepheid variables in galaxies tens of millions of light years away. Ground-based telescopes cannot resolve these stars in distant galaxies due to atmospheric blurring, making space-based observations essential for extending the cosmic distance ladder to cosmologically significant distances. But the precision required for these measurements pushes observational astronomy to its limits. Cepheid observations must account for stellar crowding, where multiple stars appear blended together at the telescope's resolution limit. They must correct for interstellar dust that dims and reddens starlight in unpredictable ways. They must distinguish Cepheids from other types of variable stars that follow different period luminosity relationships. Each of these effects introduces potential systematic errors that could bias the distance measurements. Type Ia supernovae bring their own complications. Though these stellar explosions are remarkably uniform, they show subtle variations that must be corrected to achieve the precision needed for accurate distance measurements. The brightness of Type Ia supernovae correlates with how quickly they fade after reaching peak brightness, requiring careful light curve analysis to standardize their luminosities. Environmental effects, such as the metallicity of their host galaxies, may also influence supernova properties in ways that affect distance determinations. Critics of the local measurements point to these potential systematic errors as possible explanations for the Hubble tension. Perhaps Cepheid period luminosity relationships vary with stellar population in ways not yet understood. Perhaps Type Ia supernovae are influenced by environmental factors that bias distance measurements. Perhaps the complex corrections needed for dust extinction and stellar crowding introduce subtle but systematic errors. But advocates for the local measurements argue that extensive cross-checks support their results. Different teams using different telescopes and different analysis techniques obtain consistent results. Alternative distance indicators, such as the tip of the red giant branch method and surface brightness fluctuations in galaxies, yield Hubble constant measurements consistent with the Cepheid supernova approach. The convergence of multiple independent local methods suggests that systematic errors are unlikely to explain the entire discrepancy. Meanwhile, cosmic microwave background advocates point to the extraordinary precision and internal consistency of Planck's measurements. The same data that yields the Hubble constant also determines the cosmic matter density, the curvature of space, and numerous other cosmological parameters. All these measurements fit together in a coherent picture that matches independent observations of cosmic structure formation, Big Bang nucleosynthesis, and other cosmic phenomena. The acoustic oscillation patterns in the cosmic microwave background provide particularly robust constraints because they depend on well-understood physics of sound waves in the early universe. The locations of acoustic peaks in the power spectrum are determined by the speed of sound in the primordial plasma, and the distance sound waves could travel before recombination. These physical scales provide a standard ruler that can be compared with observations to determine cosmic geometry and expansion history. Baryon acoustic oscillations in the distribution of galaxies today provide an independent check on cosmic microwave background measurements. The same sound waves that created temperature fluctuations in the ancient radiation also left their imprint in the clustering pattern of matter throughout the universe. Galaxy surveys that map millions of cosmic structures reveal the fossilized signature of these acoustic oscillations, confirming the standard ruler measurements derived from the cosmic microwave background. Yet the Hubble tension persists despite these cross-checks, suggesting that the disagreement may reflect genuine new physics rather than measurement errors. Several theoretical possibilities could explain why local and global measurements yield different expansion rates. each with profound implications for our understanding of cosmic evolution. One possibility involves modifications to dark energy, the mysterious component that appears to drive cosmic acceleration. Most cosmological models assume that dark energy behaves like Einstein's cosmological constant, maintaining constant density as space expands. But if dark energy density has changed over cosmic time, the expansion history would differ from standard model predictions in ways that could reconcile the Hubble tension. Evolving dark energy could explain the discrepancy if its density was higher in the recent past than cosmic microwave background observations suggest. Such evolution would cause cosmic expansion to accelerate more rapidly in recent epochs, leading to higher local expansion rate measurements while preserving the acoustic oscillation patterns observed in the ancient radiation. Various theoretical models predict such dark energy evolution, from rolling scalar fields to modifications of gravity itself. Another possibility involves additional types of matter or radiation that were present in the early universe but play little role today. Extra-relativistic particles, sometimes called dark radiation, would contribute to the cosmic energy budget during the radiation-dominated epoch, but become negligible as the universe expanded and cooled. Such particles would affect the expansion rate during the time when acoustic oscillations were forming, altering the standard ruler calibration derived from cosmic microwave background observations. Sterile neutrinos represent one candidate for dark radiation. These hypothetical particles would interact only through gravity, making them extremely difficult to detect directly, but their presence in the early universe would affect cosmic expansion in ways that could help resolve the Hubble tension. Other exotic particles predicted by theories beyond the standard model of particle physics could play similar roles. Early dark energy provides yet another theoretical possibility. If a small amount of dark energy was present during the radiation-dominated epoch, it would modify the expansion rate when acoustic oscillations were forming. This early dark energy would need to dilute away as the universe expanded, becoming negligible by the time of recombination, but leaving its signature in the acoustic oscillation patterns. Such behavior requires carefully constructed theoretical models, but could potentially explain the Hubble tension. Some physicists have proposed modifications to gravity itself as explanations for the discrepancy. While general relativity has passed every precision test in the solar system and through gravitational wave observations, it's possible that gravity behaves differently on cosmological scales or during certain epochs of cosmic evolution. Modified gravity theories could alter the relationship between matter density and expansion rate in ways that reconcile local and global measurements. The stakes for resolving the Hubble tension extend far beyond academic interest. If the discrepancy reflects genuine new physics, it could herald the discovery of phenomena that require extensions to our current theoretical framework. Dark energy evolution, extra-relativistic species, or modified gravity would all represent profound additions to our understanding of fundamental physics, with implications extending from particle physics to general relativity. Alternatively, if systematic errors explain the tension, identifying and correcting these errors will improve the precision of cosmic age determinations and strengthen confidence in our cosmological measurements. Either outcome advances our understanding, but the implications for fundamental physics depend critically on whether the discrepancy is observational or theoretical in origin. Future observations promise to shed light on this puzzle through multiple independent approaches. The James Webb Space Telescope, with its unprecedented infrared sensitivity and resolution, will observe Cepheid variables in more distant galaxies and provide independent checks on Hubble Space Telescope measurements. Advanced ground-based telescopes will survey millions of Type 1a supernovae to test whether environmental effects systematically bias distance measurements. Next-generation cosmic microwave background experiments will measure the acoustic oscillation patterns with even higher precision, testing whether subtle systematic effects in current measurements could explain the Hubble tension. Large-scale structure surveys will map the distribution of galaxies over cosmic history with unprecedented detail, providing additional constraints on cosmic expansion through baryon acoustic oscillations and other techniques. Gravitational wave astronomy offers completely independent approaches to measuring cosmic expansion through standard sirens. As the number of detected neutron star mergers increases, gravitational wave distance measurements, combined with electromagnetic redshift observations, will provide expansion rate determinations that don't depend on either cosmic distance ladder calibrations or cosmic microwave background physics. The Hubble tension has evolved from a minor discrepancy to one of the most important puzzles in modern cosmology. Its resolution will either validate our current understanding of cosmic evolution with unprecedented precision or reveal new physics that transforms our comprehension of how the universe ages and evolves. Either way, the tension highlights how precise measurements of cosmic time can illuminate the deepest questions about the nature of reality itself. The possibility that the universe might have two different ages, depending on how we measure them, challenges our most basic assumptions about cosmic evolution. Time itself, which seems so fundamental and universal from our human perspective, may be more complex and subtle than we imagined. The resolution of this tension may ultimately teach us not just how old the universe is, but what cosmic time itself really means. In a cosmos far stranger and more wonderful than our current theories suggest. What does it mean for the universe to have an age? This question, which might seem straightforward after 8 chapters exploring cosmic time measurement, opens into philosophical depths that challenge our most basic assumptions about existence, causation, and the nature of reality itself. The scientific achievement of measuring cosmic age with billion-year precision represents more than technical mastery. It confronts humanity with profound questions about our place in a cosmos that had a beginning and will have an end. The very concept of cosmic time forces us to grapple with the relationship between human experience and cosmic reality. Our lives unfold over decades, our civilizations over centuries or millennia, our species over hundreds of thousands of years. These timescales feel substantial from our perspective, yet they represent the briefest flicker against the 13.8 billion-year backdrop of cosmic history. If the universe's lifetime were compressed into a single year, all of recorded human history would occupy less than the final second before midnight on December 31st. This vast disparity in timescales creates what philosophers call the problem of cosmic significance. How can human existence have meaning or purpose in a universe so ancient and vast that our entire species appears as a momentary accident? The measurement of cosmic age forces us to confront our apparent insignificance against the backdrop of deep time, yet simultaneously demonstrates the remarkable capacity of finite minds to comprehend infinite questions. The discovery that the universe has an age, rather than existing eternally, fundamentally transformed human self-understanding. For most of history, people lived within conceptual frameworks that assumed the cosmos was eternal, either unchanging forever or cycling through endless repetitions. These frameworks provided psychological comfort by embedding human existence within permanent structures that gave life enduring context and meaning. The Big Bang Theory shattered this comfort by revealing that everything we know emerged from a singular moment of creation approximately 13.8 billion years ago. This cosmic birthday forces us to confront ultimate questions. What existed before the beginning? What caused the universe to come into existence? Will cosmic expansion continue forever, leading to a cold, empty future? Or will gravity eventually cause universal collapse and destruction? These questions push against the boundaries of scientific inquiry into realms that touch philosophy, theology, and the deepest human concerns about meaning and mortality. Science can measure when cosmic expansion began with extraordinary precision, but it cannot explain why anything exists at all, rather than nothing. the age of the universe becomes a precisely known boundary marker between what science can investigate and what lies beyond empirical inquiry. The role of gravity in cosmic time measurement adds additional layers of philosophical complexity. Einstein's revelation that gravity curves space-time means that time itself is not absolute but relative, flowing differently depending on gravitational environment. This relativity of time challenges common sense notions about the universality of temporal experience and raises profound questions about the nature of simultaneity and cosmic synchronization. If time flows at different rates in different gravitational environments, what does it mean to speak of the universe having a single, well-defined age? The 13.8 billion years derived from cosmic microwave background observations represents time measured by a hypothetical observer moving with the average expansion of space, free from local gravitational effects. But actual observers, embedded within gravitationally bound structures like galaxies and solar systems, experience slightly different temporal flows. These gravitational time differences are tiny under most circumstances, but they become significant near massive objects like black holes or neutron stars. An observer falling toward a black hole would experience time dilation so extreme that they could witness the entire future evolution of the universe unfold in what feels like moments to them. From their perspective, the universe would age billions of years while they aged only briefly. Which temporal perspective represents the true age of the cosmos? This relativity of cosmic time also raises questions about the meaning of simultaneity across cosmic distances. When we say the universe is currently 13.8 billion years old, we implicitly assume there exists a universal now that extends across all of space. But Einstein's relativity reveals that simultaneity is relative, depending on the motion and gravitational environment of the observer making the determination. Events that appear simultaneous to one observer occur at different times according to another observer moving at high speed or in a different gravitational field. This relativity of simultaneity means that the very concept of cosmic age depends on choosing a particular reference frame for measurement. The standard choice, commoving with the cosmic expansion, provides a natural and useful definition, but it remains a choice rather than an absolute truth. The precision with which we can now measure cosmic age also illuminates the remarkable capacity of human intelligence to transcend the limitations of individual existence. Each person lives for at most a century, observing the universe for a tiny fraction of its total history. Yet through collaboration across generations, humans have developed theoretical frameworks and observational techniques that reveal cosmic evolution over timescales, utterly beyond direct experience. This achievement represents one of the most extraordinary examples of collective human intelligence overcoming individual limitations. No single person discovered cosmic age. Instead, the measurement emerged from centuries of cumulative effort by thousands of scientists building upon each other's insights. The cosmic age measurement embodies human civilization's capacity for long-term thinking and collaborative investigation. The tools and concepts required for cosmic age measurement also demonstrate the deep unity underlying apparently disparate phenomena. The same gravitational physics that governs falling apples and planetary orbits also controls cosmic expansion and structure formation. The same quantum mechanics that operates in atomic interactions also determines the acoustic oscillations preserved in the cosmic microwave background. Measuring cosmic age requires understanding how these fundamental physical principles operate across scales spanning dozens of orders of magnitude. This unity of physics across cosmic scales provides profound reassurance about the comprehensibility of nature. The universe could have been constructed so that different regions or epochs operated according to completely different physical laws. Instead, the same principles that we can study in laboratories on Earth apply to the most distant galaxies and the earliest moments of cosmic history. This universality of physical law makes cosmic age measurement possible and suggests deep underlying order in the cosmos. Yet the measurement of cosmic age also reveals the universe's fundamental contingency. The precisely determined 13.8 billion year age depends on specific values of physical constants, cosmic densities, and initial conditions that could, in principle, have been different. If the density of dark matter were slightly higher, cosmic expansion would have proceeded more slowly, and the universe would be older today. If the cosmological constant were larger, expansion would have accelerated more rapidly and the current age would be younger. This sensitivity to cosmic parameters raises profound questions about why the universe has the particular properties that allow for its age to be measured by intelligent observers. The anthropic principle suggests that we observe cosmic properties compatible with our existence because universes with very different properties wouldn't contain observers to measure their ages. But this explanation raises additional questions about whether other universes with different properties might exist, and what determines the distribution of physical constants across possible realities. The finite age of the universe also confronts us with cosmic mortality. Just as individual lives have beginnings and endings, the cosmos itself appears to have been born and will eventually die. Current observations suggest that cosmic expansion will continue forever, with the universe growing ever colder and emptier as stars exhaust their fuel and black holes evaporate through Hawking radiation. The heat death of the universe, predicted by thermodynamics, looms in the unimaginably distant future. This cosmic mortality adds poignancy to human existence and scientific achievement. All our discoveries about cosmic age and evolution, all our artistic and cultural accomplishments, all our love and struggle and hope, appear destined for ultimate oblivion in a universe that will eventually become cold and empty. Yet this very transience may make our achievements more rather than less meaningful, precisely because they emerge from and transcend such apparently hostile cosmic conditions. The measurement of cosmic age also raises questions about the relationship between scientific knowledge and human meaning. Does knowing that the universe began 13.8 billion years ago make our lives more or less significant? Does understanding cosmic evolution enhance or diminish human dignity? Different philosophical and religious traditions offer conflicting answers to these questions, reflecting deeper disagreements about the relationship between scientific knowledge and human value. Some find cosmic age measurements profoundly humbling, emphasizing human insignificance against the vast backdrop of cosmic time and space. From this perspective, scientific cosmology reinforces themes of humility and wonderment that appear in many religious and philosophical traditions. We are temporary arrangements of matter and energy in a cosmos whose scale dwarfs our comprehension. Others find cosmic age measurements deeply empowering, celebrating the capacity of human intelligence to comprehend cosmic evolution despite our apparent insignificance. From this perspective, the measurement of cosmic age demonstrates that consciousness and intelligence are remarkable emergent properties of cosmic evolution, capable of understanding the very processes that brought them into existence. The universe becomes self-aware through the scientific investigations of the intelligent beings it has produced. The social and cultural dimensions of cosmic age measurement reveal how scientific discoveries interact with broader human concerns about meaning and identity. Different societies and historical periods have interpreted cosmic time measurements through the lens of their existing beliefs and values, finding in cosmic age either confirmation or challenge to their worldviews. Religious communities have responded to cosmic age measurements in diverse ways, some finding compatibility between Big Bang cosmology and creation narratives, others seeing conflicts between scientific and theological accounts of cosmic origins. These responses reflect deeper questions about the relationship between scientific and religious knowledge. and whether cosmic age measurements have implications for theological questions about divine action and cosmic purpose. The global nature of cosmic age measurement also highlights how scientific knowledge transcends cultural and political boundaries. The 13.8 billion year age of the universe represents a shared human achievement that belongs to no single nation or tradition. Cosmic microwave background observations from European satellites, gravitational wave detections from American observatories, and theoretical insights from scientists around the world all contribute to our understanding of cosmic time. This international character of cosmic age measurement provides hope for human cooperation on challenges that transcend national boundaries. If humanity can collaborate to measure the age of the universe with billion-year precision, perhaps we can also work together to address climate change, poverty, disease, and other global challenges that require coordinated action across cultural and political divisions. The educational implications of cosmic age measurement are equally profound. Teaching about cosmic time requires helping students grasp timescales and physical processes utterly beyond everyday experience. How do we help young minds comprehend 13.8 billion years when their own lives span only a decade or two? How do we convey the precision and beauty of cosmic age measurements while acknowledging the profound mysteries that remain unsolved? These pedagogical challenges reflect deeper questions about how scientific knowledge relates to human understanding and wisdom. Measuring cosmic age represents extraordinary technical achievement, but translating that measurement into broader human understanding requires bridging the gap between precise scientific knowledge and the lived experience of meaning, purpose, and significance that shapes individual lives. The philosophical dimensions of cosmic age measurement ultimately return us to fundamental questions about the relationship between human consciousness and cosmic reality. We are arrangements of matter and energy that emerged through cosmic evolution, yet we possess the remarkable capacity to understand the very evolutionary processes that created us. This reflexivity, this capacity for cosmic self-awareness, may represent one of the most significant developments in the 13.8 billion year history of the universe. Gravity, the force that governs cosmic expansion and enables cosmic age measurement, also created the conditions for complexity, structure, and ultimately consciousness to emerge from cosmic evolution. In measuring cosmic age through gravitational effects, we are using products of cosmic evolution to understand cosmic evolution itself. The universe becomes self-aware through scientific investigation, measuring its own age through the collective intelligence of the conscious beings it has produced. We stand at the edge of a precipice, gazing into an abyss of the unknown that could contain the ultimate answer to existence itself. Behind us lies more than a century of revolutionary discoveries that have transformed our understanding of light, gravity, space, and time. Ahead lies the possibility of a final theory that could unite these concepts in a framework so elegant and complete that it would represent the culmination of humanity's quest to understand the cosmos. The dream of a theory of everything isn't just about satisfying scientific curiosity. It's about answering the deepest questions that have haunted human consciousness since we first looked up at the stars and wondered about our place in the universe. Why does anything exist at all? Why do the laws of physics have the particular forms they do? How did the universe begin, and how will it end? Is reality fundamentally mathematical, computational, or something else entirely? A successful unification of light speed and gravity would provide more than just mathematical elegance. It would unlock secrets that could reshape our understanding of black holes, revealing what happens to information that falls past the event horizon, and whether these cosmic monsters eventually evaporate completely through Hawking radiation. It might tell us whether the Big Bang was truly the beginning of time or merely a transition from some previous state of existence. Such a theory could revolutionize our understanding of consciousness itself. Some researchers have speculated that consciousness might emerge from quantum processes occurring in the brain, processes that could be influenced by the gravitational field created by neural activity. If consciousness is indeed connected to quantum gravity effects, then a theory that unifies these phenomena might provide insights into the nature of awareness, thought, and subjective experience. The technological implications could be staggering. A complete understanding of quantum gravity might reveal new ways to manipulate space-time itself, potentially leading to technologies that seem impossible today. We might learn to create artificial gravitational fields, bend space and time at will, or even access the energy locked away in the quantum vacuum. The leap from our current understanding to a theory of everything could be as transformative as the leap from classical mechanics to quantum mechanics and relativity. But perhaps most importantly, a unified theory would complete Einstein's vision of a cosmos governed by beautiful, comprehensible mathematical principles. It would show that beneath the apparent complexity and chaos of the universe lies a deep order that connects the smallest quantum fluctuations to the largest cosmic structures. The speed of light wouldn't just be an arbitrary limit, but would emerge naturally from the fundamental structure of reality itself. Yet the journey toward this ultimate theory has revealed just how strange and counterintuitive reality might be at its deepest level. The comfortable assumptions of classical physics, where objects have definite positions and properties independent of observation, have given way to a quantum world where measurement creates reality and particles can exist in multiple states simultaneously. The smooth, continuous space-time of general relativity might itself be an illusion, hiding a discrete, granular structure that operates according to rules we're only beginning to glimpse. Space and time, which seems so fundamental to our experience, might emerge from something even more basic, perhaps the quantum entanglement of pure information. The forces we observe, from the electromagnetic force that governs light to the gravitational force that shapes cosmic evolution, might all be aspects of a single, unified phenomenon, operating in dimensions we cannot directly perceive. The particles we think of as fundamental might be vibrating strings, loops of quantum geometry, or emergent patterns in a vast computational process. Even our concepts of existence and non-existence might need revision. The multiverse theories suggest that reality might be far vaster than our observable universe, containing an infinite number of regions with different physical laws and constants. In such a reality, our particular combination of light speed and gravity might be just one possibility among countless others. The pursuit of unification has also forced us to confront the limits of human knowledge and understanding. Some aspects of reality might be fundamentally incomprehensible to minds that evolved to navigate the classical world of everyday experience. We might be like two-dimensional beings trying to understand three-dimensional space, capable of detecting shadows and projections, but unable to fully grasp the underlying reality. Yet even if complete understanding proves elusive, the search itself has already transformed our world. The quantum mechanics developed in the quest to understand atomic structure has given us computers, lasers, and magnetic resonance imaging. General relativity, born from Einstein's attempts to understand gravity, enables the global positioning system and provides crucial corrections for satellite communications. String theory, despite remaining experimentally unconfirmed, has revolutionized mathematics and led to new insights about the deep connections between geometry, topology, and physics. Loop quantum gravity has provided new perspectives on the nature of space and time that might ultimately prove crucial for understanding the quantum world. The experimental techniques developed to search for quantum gravity effects have pushed measurement precision to previously unimaginable levels. gravitational wave detectors can measure distortions smaller than 1/10,000th the width of a proton. Atomic clocks are so precise they would lose less than a second over the age of the universe. Quantum optics experiments can manipulate individual photons and create entangled states that span continents. These technological advances have applications far beyond fundamental physics. Precision measurement techniques developed for testing general relativity have led to improvements in navigation, communication, and timekeeping. Quantum technologies emerging from the study of quantum gravity might eventually lead to quantum computers capable of solving problems that are impossible for classical machines. The search for dark matter and dark energy has driven the development of ever more sensitive detectors and telescopes. These instruments are revealing the universe in unprecedented detail, from the cosmic microwave background radiation that preserves information about the universe when it was only 380,000 years old, to the gravitational waves that carry messages from the most violent events in cosmic history. Each new observation provides pieces of the puzzle, gradually revealing the underlying patterns that connect light and gravity. The fact that gravitational waves travel at exactly the speed of light hints at a deep connection between space-time geometry and electromagnetic phenomena. The holographic principle suggests that information, rather than matter and energy, might be the fundamental constituent of reality. The emergence of quantum information science has provided new tools for thinking about these deep questions. Concepts like quantum entanglement, quantum error correction, and quantum computation are reshaping our understanding of how information flows through quantum systems and how complex phenomena can emerge from simple underlying rules. Some researchers now suspect that the universe might literally be a quantum computer, processing information about its own state according to the laws of physics. In this view, particles, forces, and space-time would all be different aspects of an underlying computational process, and the unification of physics would be equivalent to understanding the fundamental algorithm that governs reality. This computational perspective offers new ways to think about old problems. The fine-tuning of physical constants might reflect the optimal parameters for stable computation. The arrow of time might emerge from the irreversible flow of information through quantum systems. The apparent randomness of quantum mechanics might arise from the computational complexity of tracking all the correlations in a truly vast quantum system. But even as we develop these new perspectives, fundamental questions remain. Why does mathematics describe the physical world so accurately? Is this because reality is fundamentally mathematical? Or because mathematical thinking is the only way minds like ours can comprehend complex patterns? Are the laws of physics discovered or invented? Do they exist independently of conscious observers? Or are they somehow dependent on the act of observation itself? The anthropic principle raises equally profound questions about the relationship between physical law and conscious experience. The fact that the universe appears fine-tuned for the existence of complex structures, like stars, planets, and life, might be explained by the existence of multiple universes with different properties. But this raises the question of whether consciousness itself plays a fundamental role in selecting which universe we experience. Some interpretations of quantum mechanics suggest that consciousness might indeed play a crucial role in determining physical reality. If this is true, then a complete theory of everything might need to incorporate not just the laws that govern matter and energy, but also the principles that govern awareness and observation. The quest for unification has also revealed the importance of symmetry in fundamental physics. The electromagnetic and weak forces are unified through gauge symmetry. General relativity emerges from the requirement that the laws of physics be the same for all observers. String theory relies on supersymmetry to maintain mathematical consistency. These symmetries aren't just mathematical conveniences, they seem to reflect deep truths about the structure of reality. A final theory might reveal that all the apparent diversity of physical phenomena arises from the breaking of some fundamental symmetry, like different notes emerging when the perfect silence of the vacuum is disturbed. Yet symmetry breaking also introduces an element of contingency into physics. If the fundamental laws are symmetric, but reality, as we observe it, is not, then the particular way symmetry was broken in our region of space and time might be accidental rather than inevitable. This suggests that even a theory of everything might not predict all the details of our observable universe. The relationship between determinism and randomness in fundamental physics remains another deep mystery. Quantum mechanics introduces genuine randomness into the description of individual events, even though it makes precise statistical predictions about large numbers of events. Whether this randomness reflects fundamental indeterminacy or merely the limitations of our current understanding remains hotly debated. A theory that successfully unifies light speed and gravity might resolve this question by revealing whether quantum randomness is truly fundamental or emerges from some deeper deterministic process. Alternatively, it might show that the distinction between determinism and randomness is itself an artifact of our limited perspective on a reality that transcends both. As we look toward the future, several pathways toward unification seem promising. String theory continues to evolve, with new mathematical techniques revealing previously hidden connections between different versions of the theory. Loop quantum gravity is making contact with cosmological observations and black hole physics in ways that might soon lead to testable predictions. Emergent gravity theories are beginning to make specific predictions about deviations from general relativity that could be tested with future experiments. The holographic principle is leading to new insights about the nature of information and its relationship to space-time geometry. Quantum error correction is providing new tools for understanding how stable structures can emerge from quantum mechanical systems. The convergence of these different approaches suggests that we might be approaching a breakthrough comparable to the revolutions that gave us quantum mechanics and general relativity. But unlike those earlier revolutions, which could be understood largely through the work of individual geniuses, the coming synthesis will likely require the collaborative efforts of researchers from many different fields. The theory of everything, when it comes, might not look like what we expect. It might not be a single equation, but a vast computational framework. It might not predict specific outcomes, but describe the space of all possible realities. It might not answer our questions about the meaning and purpose of existence, but reveal that these questions are based on false assumptions about the nature of reality. Whatever form it takes, the ultimate theory will represent the culmination of humanity's greatest intellectual adventure. From the first humans who wondered about the lights in the sky, to the modern physicists probing the quantum nature of space-time, we have been engaged in a collective effort to understand our place in the cosmos. If light speed and gravity are indeed two languages describing the same underlying reality, then learning to speak their common tongue will be like achieving literacy in the fundamental language of existence itself. We will finally be able to read the universe as a book written in the language of mathematics, quantum mechanics, and geometry. The journey toward this understanding has already shown us that reality is far stranger and more wonderful than our ancestors could have imagined. Space and time are not fixed stages, but dynamic players in the cosmic drama. Matter and energy are interconvertible aspects of the same phenomenon. The act of observation can influence the reality being observed. The final theory, when it emerges, will likely reveal even greater wonders. It might show us how to transcend the apparent limitations of space and time, how to access information from the quantum vacuum, or how to manipulate the fundamental forces that govern reality. It might reveal connections between consciousness and physics that transform our understanding of what it means to be aware, thinking beings in a quantum universe. But perhaps the greatest wonder of all will be the simple fact that such a theory exists, that the universe is comprehensible to minds like ours, that the mathematical patterns we discover in our equations correspond to the deep structures of reality itself. In achieving a theory of everything, we will have completed the circle that began when the first conscious beings looked up at the stars and began to wonder why they shine. The universe, in learning to understand itself through us, will have achieved a kind of cosmic self-awareness that represents the ultimate triumph of intelligence over ignorance, of light over darkness, of understanding over mystery. And in that moment, the ancient dream of unification will be fulfilled, not just as a scientific achievement, but as a spiritual awakening to the profound interconnectedness of all existence.